This is KJ here, going over 3.09 Part 2 Colligative Properties. Alright, so we are talking about how the vapor pressure drops because, again, there's molecules of solute in the way. The number of moles of solute is the key factor in determining the effect of a solvent's colligative properties. The quantitative measure of colligative properties, such as boiling point elevation, freezing point depression, and vapor pressure lowering, depends on the number of solute particles, not their actual chemistry. We don't care if it's sugar or salt. Chemically, sugar and salt are crazy different, and we don't care which one it is. Hey, we just care how many moles we have. Now, this fact may be counterintuitive. It seems that colligative properties would be related to the chemical nature of the solute being used, but that is not the case. When sugar or salt is added to water, the freezing point decreases and the boiling point increases. The key quantity is the number of moles of solute. Sugar does not dissociate in water. It stays together as a single molecule. So 1 mole of glucose contributes only 1 mole of substance to the solution. 1 mole of NaCl in solution contributes 2 moles of substances. 1 mole of Na and 1 mole of Cl, therefore a molar amount of NaCl will have twice the effect on a solution's colligative property as an equal molar amount of sugar. Alright, so if you're thinking to yourself, wait a minute, you just told me all that mattered was how much. Yes, but when you put sugar in water, it stays C2H4O2 or C6H12O6, whatever type of sugar it is. It stays that one big clump, so you have 1 mole of these. Salt completely breaks into the Na and the Cl ions, and so you have a mole of Na and a mole of Cl. Just like if this broke apart, you would have 2 moles of carbon, 4 moles of hydrogen, 2 moles of oxygen, but it doesn't. So this stays as one big clump, so you have 1 mole of these, whereas salt, you have 2 moles because basically it's split in half. You started out with 1 mole, but now you have a mole of these, a mole of those. Just so you know, salt and sugar are the only substances I'm going to quiz you on or test you on as far as this section goes. If I used 1 mole of salt in 1 kilogram of water, what would the freezing point become? So let's look at some math. Colligative properties are unique for each solvent. Each solvent has its own K, or K is the variable that we use, for how the addition of specific amounts of solute will change the freezing point, boiling point, or vapor pressure. The units for K are degrees Celsius per molal, where lower italicized m is the molal concentration of the solution. For example, for every mole of solute, the freezing point of 1 kilogram of water will change by negative 1.86 degrees Celsius. So that means every time you put a mole of anything in water, the freezing point is going to drop by almost 2 degrees. You can calculate the effect of a solute on a solvent's temperature by multiplying the K value by the molality M. For example, elevation and boiling point, so how much the boiling point goes up, change in temperature, equals K sub B times lowercase italicized m, or molality. Depression and freezing point, same idea, except now you're doing the freezing point. This shows over here that different substances are affected differently. So water drops about 2 degrees in the freezing point for every mole of solute that you add. Acetic acid drops by how much? Almost 4 degrees. Benzene drops by 5 degrees. Phenol drops by 7 degrees. All, if you add the same 1 molal of solution, it doesn't matter, they drop different amounts. Look at their boiling points. Now the boiling points increase. So when we go back to here, here's original melting or freezing point, and that gets lowered. Here's our original boiling or condensing point, and that gets higher. So these are the originals, the inside ones. The outside ones are what it becomes because of the colligative properties. All right, so let's look at our problem, which I did change to sugar. I'm not going to try and trick you guys on this whole dividing up. We're just going to use sugar the whole time, okay? So we're just going to use sugar. You don't have to worry about if it splits up into 1 mole or 2 moles or 15 moles. It's just, when I say 1 mole, I just mean 1 mole. All right, so If I used 1 mole of sugar in 1 kilogram of water, what would the freezing point become? So I use our equation T sub F, or the freezing temperature, equals K sub F times M, lowercase, italicized. And what numbers are we going to put in? Well, what's the K value for water, the K sub F? We look over here, it's negative 1.86. And how many molal do we have? 1. So we get negative 1.86. Water freezes at 0 degrees Celsius. So 0 minus 1.86 equals negative 1.86 degrees Celsius would be the temperature that the water would freeze at. Okay, what about if I had 3 moles? So hit pause, get your answer. So again, we're doing water. So we would use the K sub F value of negative 1.86 times 3 gives us negative 5.58. Subtract the fact that water freezes at 0 degrees Celsius. Our new freezing point is negative 5.58. Now, if you're like, really, do I have to subtract it from 0? For water, obviously no, but different substances have different freezing points. So if the freezing point was, let's say, 10, then that's going to change my answer, right? Because now I would have to actually do the math and say 10 minus 5.58, my new freezing temperature would be positive 4.42. So again, this is if it was a different chemical. So if a different chemical froze at 10 degrees. But again, water freezes at 0. Okay, if I use 3 moles of sugar in 1 kilogram of water, what would the boiling point become? All right, so we're using T sub B equals K sub B times M. And what numbers would you put in? 0.512. I'm using the boiling point, so I would use that, times the fact that I have 3 moles per kilogram, so 3 molal, and it equals 1.57. What's my final answer? Remember, I want to know what the boiling point would be. What does water normally boil at? 100 degrees Celsius. So my new boiling point would be 101.57 degrees Celsius when it boils. All right. So, colligative properties. Physical properties can be divided into 2 categories. Extensive properties, such as mass and volume, depend on the size of the sample. Intensive properties, such as density and concentration, are characteristic properties of the substance. They do not depend on the size of the sample being studied. Okay, so that's okay. You don't need to know these words. It was just kind of some extra background for you. This section introduces the third category, that is the subset of the intensive properties of the solution. The third category is the colligative properties, and it can only be applied to solutions. By definition, one of the properties of a solution is a colligative property if it depends only on the ratio, the amount of the number of particles of solute and solvent in the solution, not the identity of the solute. So again, we don't care if it's salt or sugar and water, we only care how much solute we have. So this was just a different way of explaining what colligative properties was. And again, this should be a little bit of a review on this slide. When the temperature of a liquid is below its boiling point, we can assume that only the molecules that can escape from the liquid to form a gas are those that lie near the surface of the liquid. So evaporate, right? You have to be at the top to evaporate. When a solute is added to the solvent, some of the solute molecules occupy the space near the surface of the liquid as shown in the figure below. When a solute is dissolved in a solvent, the number of solvent molecules near the surface decreases and the vapor pressure of the solvent decreases. This has no effect on the rate at which the solvent molecules in the gas phase condense to form a liquid, but it decreases the rate at which the solvent molecules in the liquid can escape to become a gas. As a result, the vapor pressure of the solvent escaping from a solution should be smaller than the vapor pressure of the pure solvent. So that basically goes to explaining boiling point elevation and freezing point depression. And this is a figure that we've been referring to. Okay, so I'm not going to go more into this on the quiz by any means, but I just thought it was a little something interesting to help explain the why of it. The figure below shows the consequences of the fact that solutes lower the vapor pressure of a solvent. The solid line connecting points B and C in this phase diagram contains the combination of temperatures and pressure at which the pure solvent and its vapor are at equilibrium. Each point on this line therefore describes the vapor pressure of the pure solvent at that temperature. The dotted lines in this figure describes the properties of a solution obtained by dissolving a solute in the solvent. At any given temperature, the vapor pressure of the solvent escaping from the solution is smaller than the vapor pressure of the pure solvent. The dotted line, therefore, lies below the solid line. According to this figure, the solution can't boil at the same temperature as the pure solvent. If the vapor pressure of the solvent escaping from a solution is smaller than the vapor pressure of the pure solvent at any given temperature, the solution must be heated to a higher temperature before it boils. The lowering of vapor pressure of the solvent that occurs when it is used to form a solution, therefore, increases the boiling point of the liquid. So this is just, again, explaining more of the how and the why. Colligative properties depend on the number of moles of solute particles. Can you tell that's important since I've said it like 5 times? Colligative properties do not depend on the chemical nature of the solute, but on how many moles of solute are added to a solvent. Colligative properties include boiling point elevation. Elevation means go up. Vapor pressure lowering, and freezing point depression. Depression means it gets lower. All right, go ahead and do the pre-quiz, and if you have questions on anything, let me know.